Okay, we are continuing with chapter 1. We will now discuss photoelectric effect. Here is a sheet of metal. It's a solid. We regard the sheet of metal as a collection of electrons and nuclei. So let us indicate the electrons by such a symbol. Our common view of electrons in a metal is such that the electrons are relatively free to move inside the metal. Of course, there are positively charged nuclei which are keeping the electrons inside the metal. Now, in the photoelectric effect, such a metal sheet is illuminated by light. So let us indicate by this curvy symbol, light, with some frequency so that the photon energy is h times nu. This is visible or UV light. It is observed that electrons from the metal can be ejected when the surface is illuminated by light. And let us indicate the ejected electrons. These are the ejected electrons in this experiment are called photoelectrons. Obviously, the name comes from the fact that these are ejected electrons as a result of shining by some light. Now, the experiment is done in the following way. There is a source which generates the light, and the source is capable of changing the frequency of the light. At low frequencies of light, no photoelectrons are produced. Only at high frequencies of light, photoelectrons are generated. There is a starting value for the frequency of light, which causes electrons to be ejected. That one we will indicate by the minimum. This is the minimum light frequency that can cause photo ejection. If the light frequency is larger than this minimum value, then photoelectrons are produced. And this is the minimum value at which photoejection starts. For frequencies smaller than the minimum frequency, no electrons are ejected. These are the experimental observations. The experimental technique which is used is capable of, here there is a detector. Detectors I will represent always as I. Okay. This detector can measure the speed of the ejected electrons and also number of ejected electrons. So measuring speed is the same thing as measuring kinetic energy of the ejected electrons, because there is a simple relation between speed and kinetic energy. Kinetic energy is equal to 1/2 mass times v square. So you may regard the detector, detecting instrument, as measuring the kinetic energy of the ejected electrons and also their numbers, how many are ejected, as a function of frequency. At each frequency, these things will change. Okay, now how to interpret, how to theoretically justify what's happening here. Well, the electrons inside the metal are trapped into the metal, and just like any other substance, these electrons will have a set of allowed energy levels. So let us show them. These are allowed energy levels of an electron inside a metal. We are considering all possibilities for the energy levels of the electron. The total set of electron levels can be characterized as two parts. One part is the quantized part, starting with this is the ground level. Then there are excited energy levels. Let us number them: E2, E1, E3, and here I have put 3 dots. This means it continues like that. The nature of the quantized energy levels is that as energy goes up, spacing between one level and the next one, that decreases. It means that the difference between E2 minus E1 is larger than E3 minus E2, or in the opposite way, if we express it, E4 minus E3 is smaller than E3 minus E2. And this is smaller than E2 minus E1. So as energy goes up, the energy levels start approaching each other, such that there is a certain energy And these energy levels become very near. At this value for the energy, the difference between neighboring levels is very, very tiny. And after this, energy levels become continuous. This is the start of continuum. I will give, this means continuum, E continuum. In fact, E continuum, you may say, this index which counts, which labels the discrete energy levels as 1, 2, 3, 4. When we come to here, the index value becomes infinite. This is the quantized energy levels. Of course, there is no upper limit for the possible energy of the electron. The energies after this E continuum are all continuous. Okay. Now, in a normal metal, in its normal state, we may assume all the electrons are in their ground states. So the ground level is the initial energy level. For these photoelectrons. In other words, the electrons which are ejected are ejected from the ground level. Now, the quantized, when the electron is in any one of these quantized levels, we interpret it as the electron is trapped inside the metal. In other words, when the electron is one of these even excited energy levels, it is not ejected. It stays inside the metal. But as energy goes up within the quantized part, the electron with that energy goes farther and farther away from the nearest positive charges. But the electron is still captured because positive charges are effective. We need energy to overcome the effect of positive charges in order to eject it. When the energy gets nearer to this E continuum, we imagine the electron to be near the surface of the metal, but still attracted by the nuclei on the surface of the metal. When the energy is exactly at E continuum here, the electron is somewhat away from the surface, such that the net forces which attract the electron becomes zero. And after this value, electron becomes free, which means it is sufficiently far away from the surface, and the net electric charges attracting the electron is 0, and the electron has only kinetic energy moving away. Those are the photoelectrons then. So let us say that if the photon energy, which is h times frequency of this light, is larger than this difference. First, let us write this one. This is E continuum minus ground energy level. This is the minimum energy which is needed to ionize the electron, which is initially in this energy level, E1. The circumstance is that with this energy, E continuum minus E1 energy, the electron is just ejected. It has 0 kinetic energy. All right? And this is the minimum possible energy to cause photoejection. This energy difference is given the symbol W, and it must be equal to the h Planck's constant times the minimum frequency, which is experimentally observed, which causes ejection of the electron. If the energy is larger than or the frequency, you see, photon energy is directly proportional to frequency. So larger frequency means larger photon energy. So if the energy is larger than the minimum energy which is needed to cause photoemission, then the extra energy, extra from that value, is used in speeding up the electron, so electron gains kinetic energy. Such a situation is, say, let us say this is the photon energy, h times nu, is large enough, and it is equal to this value. Which symbol did I use for it? E prime. E prime has a larger value than E continuum, as this diagram shows you. If the photon energy is that much, which is equal to E prime minus E1, the electron will make a transition from this level to that level when it absorbs the photon with that frequency. Now, this expression, we may write it as E prime minus E continuum. In other words, the energy difference between that level and that level is equal to this difference plus that difference, isn't it? from the diagram, it should be obvious that this. Now, this quantity, we called it W. It is this minimum energy which is needed to. And this part is the extra energy which is transferred to the electron. This electron is a free electron because it is sufficiently far away from the surface of the metal. It only has kinetic energy. There are no forces trying to pull it back. It has been released from the surface. So this part is just kinetic energy. This is mass of electron. And v is the speed of the ejected electron. So the final expression we have is, this is, let us say, light, h times frequency of the light. This is equal to kinetic energy of the ejected electron plus this minimum energy needed to cause the photoejection. Please note that minimum energy needed to eject the electron is not ionization energy. Why? Because definition of ionization energy requires a single atom. Ejection of an electron from a single atom or a molecule. But here, we do not have a single atom in the sheet. What is this? It's a solid sheet metal. So therefore, a meaning of W sounds like ionization energy, but it doesn't fit to the our chemical definition of ionization energy. It is ionization from a solid, from a metal. All right? Okay. Einstein was the first person who explained the photoelectric effect, which is this one, photoejection of electrons, in this way. You see, the idea is quite simple, and he obtained this expression, and Einstein received Nobel Prize for just this explanation, photoelectric effect. The same experiment, shining light and observing whether electrons are ejected or not, can be done. Instead of using a metal sheet, we can take a container. Substance in gas phase. The particles inside the container can be atoms, such as helium gas, argon gas, or molecular gases like O2, nitrogen gas, N2. And then here too, as a result, electrons can be ejected. the difference between the classical photoelectric effect and this type of experiment is, in the classical photoelectric effect, metal sheets are used. For instance, copper sheet, gold sheet, silver metals are used. In such experiments, we have a container, glass container. It is filled with a gas, either atomic substance or some molecule. And then just change the frequency of the light and send it to see if electrons will be ejected or not, collect them, just as in using a metal. In this case, the only difference is that from the interpretation, same expression is available. With the only difference is in interpretation of W. In that type of experiment, W is the chemical definition of ionization energy, because the electrons are ejected from single atoms or single molecules. Right? Otherwise, everything is exactly same as in the classical, the standard photoelectric effect. There are instruments which are used to study, which are used in such experiments, and the name is photoelectron spectroscopy, or short. You have already heard of UV spectroscopy, right? There, UV means ultraviolet, short. You have also heard of infrared spectroscopy, IR. Similar to that, PES, PES, photoelectron spectroscopy, short term to mean photoelectron spectroscopy. And this spectroscopy is used to find out the energy levels of the numerical values of the energy levels in the core orbitals in atoms and molecules. So it's a useful spectroscopy, and it's a modern day instrumentation. All right, let us consider exercise 2 of this chapter as a numerical example. Now, for consider as hydrogen atom, just one hydrogen atom. This hydrogen atom has a proton with +1 charge and an electron moving around it. Electron has a -1 charge. Now, the allowed energy levels of the electron in the hydrogen atom are known and given by a very simple formula. And R is a constant. R is in electron volt energy unit, 13.6 eV. This expression gives relative values of E1, E2, E3, E4 in the quantized part. All right? For the hydrogen atom, allowed energy levels of the electron. All right. In part A, the question is, what is the ionization energy of hydrogen atom? Using this information, I consider ionization the phase indication gas. It simply means that one hydrogen atom, and this is one H plus atom, which means just a pure proton, and this is the ejected electron. Plus signs between chemical symbols means that the particles are very far away from each other. All right? For instance, when you write H plus electron, it means that the cation is, if it is here, if the cation is here, the electron is very far away from it. The plus sign. It's true for all chemical equations. All right. Now, this is the ionization process. So, what is the ionization energy? Energy needed to cause this reaction, total energy of the products minus the total energy of the reactants. That's using chemical explanation, the meaning of ionization energy, isn't it? Now, the definition also requires that the ejected or the products should have zero kinetic energy. In other words, we are looking for the minimum energy which is necessary to cause this reaction. That means kinetic energy of the electron will be set to zero. Kinetic energy of the cation will also be set to zero. So here, the total energy, we may simply set zero, minus the energy of the reactant. In this case, reactant is a hydrogen atom with this energy, ground level. And the ground level is, what is it? E1 minus R. So, ionization energy is equal to just minus E1, which is equal to R, or 13.6 electron volts. According to this, you may regard the, instead of using this picture, but I think such a picture is generally more valid. You may also view it as how much energy is needed if the electron is initially at this energy level, ground level, to cause ionization. Ionization means that the minimum energy needed is this E continue, all right? E continue means then this energy, E infinity minus E1. If you put infinity here, you get zero. And minus E1, it is the same expression. So, ionization energy of hydrogen atom is 13.6 electron volts. Now, let us look at also the second part. if an X-ray photon with wavelength 8.2 nanometers, if in this experiment the light which is used, which to shine on the sample is an X-ray with this lambda value, then what will happen? And if this photon energy is larger than this value, then electron will be ejected. The extra energy will be seen as kinetic energy of the electron. So we first find out how much energy does this photon have. It has 151.2 electron volt energy. How do you calculate photon energy? H times frequency. So you need frequency of the light, but from this data, frequency is equal to C over lambda. And then you multiply with H, and you convert it into electron volt unit. It is 151.2 electron volt. Is this energy enough to cause ionization? You need only 13.6 eV, but that photon has much larger energy. So the electron will be ejected. Then this quantity will be ionization energy. You will put 13.6 eV here. The photon energy is 151.2 eV, which is here. Then you will get the kinetic energy. So kinetic energy is 50 minus 13.6 eV. And this is 137.6 eV. So this is quite a simple calculation here. Now, if the question also asks, what is the speed of the ejected electron, then, of course, you will use this. Kinetic energy equals 1/2 mass of electron times v square. In using such expressions, units must be consistent. All right? The unit for energy on the left side is electron volt here. But value for mass of electron, for example, and you will want unit of speed to be meter per second. These are SI units, all right? Therefore, you cannot directly substitute this number to the left side, but make sure the left side should also have SI unit, because the right side has SI units. What is the SI unit for energy? Joule. Therefore, you will convert this number to joule. How? Multiply it with this is the conversion factor. Notice that this number is exactly the same number as magnitude of charge on electron. That's the conversion factor from electron volt to joule. So after multiplication, put it here. Now, the left side and the right side have the same set of units, consistent units. Then you may directly use this value and obtain v square, then take the square root of and obtain v itself. So this way, when we do the calculation, we get 6.96 times 10 to the 6 meter per second. Please note that this is a very high speed. In fact, this speed is 1 over speed of light divided by 43. So approaching the maximum possible speed, in other words, of C. All right. So let us now consider or discuss what happens if a substance or atoms or molecules absorb light energy. We know they are excited to an upper state, but are they going to stay there? Excited atoms or excited molecules. Experiment shows that excited states are not stable. Excited states do have a non-zero lifetime. Lifetimes, for example, to give you an example, 1 nanosecond. That time for us is very small, isn't it? Nanosecond, 10 to the minus 9 second. But just remember that the electrons or atoms are also very small particles. And that type of time, 1 nanosecond, is not so small for them. Such times are called lifetime. Lifetime always indicates that there is an end to it. Death is inevitable. In this case, death means simply losing the energy and going to some stable state. The only stable state is the ground state. So every particle, every substance, if initially it is excited to a higher energy level, eventually ends up with the ground state, and in doing so, it has to release the extra energy it has. And the mechanism of energy loss, there are several mechanisms, but here in this course we are talking about radiative mechanisms. Radiative mechanism means loss of energy by emitting photons, by releasing photon energies. So let us draw a diagram to show the situation. Imagine this is a container. It's filled with a substance in the gas phase. The substance can be either atomic type or molecular type. For example, O2 molecules or chlorine Cl2 molecules. The symbols are that something has happened to the sample before it came to this situation. It has absorbed energy from an outside source, such that some of the atoms or molecules, which are indicated by the star here, are in excited states. All right? please note that if you have a sample, it contains nearly Avogadro's number of molecules or atoms. When you give energy, you cannot energize all of it. You can only energize some of it. What does it mean? After taking the energy, absorbing the energy, only some of the molecules are in the excited state, but the majority will be in their normal ground state. So this is indicating something like that. Now, these are already normal A molecules, which means they are in the ground state. But the star ones are in excited state. These excited atoms they have only a finite lifetime, like 1 nanosecond. After 1 nanosecond, it will give out the extra energy it has. The final address is the ground level. We indicate that by such a chemical notation. So when you look at the product side, you see there are two products. One is A, but the notation indicates that this A is the same molecule, but with a lower energy in the ground level, right? And there is also H times nu. This means a photon, a single photon has been emitted. The frequency of the photon is nu. So now the total energy requirement, this is this time initial energy. This is final energy, and this is H nu. These have to be the same. Total initial energy must be equal to total final energy of the system. Not just A, but there is also there is a photon here. So this means that the photon energy must be equal to initial energy minus final energy. Please remember, initial energy is larger than final energy. So this difference, EI minus E final, is a positive number. Of course it must be a positive number because H times nu is always positive. This gives us the total. Let us have a very simple example and then we give a break. I will indicate 1, 2, 3, 4 energy levels. Let us say this molecule A is in this excited state initially. What are the possibilities for final energy level? As a result of emission. Could it go to the higher energy levels? No, because there is no source which helps it. This is not absorption. We have just this sample. It contains some excited molecules. The only chance they have is to emit. Emission means losing energy. So final state could be either E2, it has lower energy, or E1. So let us indicate. This is one possibility. In this case, what is the photon energy? E3 minus E2, isn't it? This will be the photon energy which is emitted. Another possibility is transition to the lowest level, E1 level. In this case, photon energy will be E3 minus E1. I have indicated this as, and this one 3. The photon frequencies of the emitted photons are different, you see, because the difference E3 minus E2 is not the same as E3 minus E1. In fact, the diagram shows E3 minus E1 is larger than E3 minus E2. Therefore, this photon energy is smaller than that photon energy. So these are two possibilities. But there is also one more possibility. You have to think about what will happen to this atom. It still has higher energy than the atom when it makes a transition to here. That it is still in an excited state. All right, and this state is also unstable. It has a finite non-zero lifetime, but after that lifetime, it will make a transition to the ground level. So we have one more photon frequency available, which is E2 minus E1. All right, let us take a 10-minute break and join